I met with them during the second.
Uh, Good afternoon. I'm sorry. Yeah, afternoon. Good afternoon, everyone. I want to welcome you to another week, and of course, this week we got a lot to do, and I need you to pay attention. Just like what I said the other time, uh, there may not be opportunity for make up for me time too, and that is the reason why you need to listen good and ask questions where necessary. I told you the other time, statistics is like a story that goes on and on and on. I remember last week on Friday, um, we started, I think Wednesday, we started the family of continuous probability distribution. Of course, earlier uh, in the week, I actually introduced you to two families of probability distribution. Okay, we got family for continuous, we got family for discrete. Of course, we have walked you through every member, some selected members in the discrete family, and we started continuous family the other time. So I've walked you through the normal distribution. We've talked about normal approximation to binomial. And of course, today we're going to continue from that. If you take a look at today's topic, I call that continuous probability distribution beyond normal. So, which means other than normal distribution in a continuous family of distribution, we got other members. And today we're going to be focusing on other members of the family. Now, in the outline, um, the first member we're going to visit today after normal is uniform. Then from there, we're going to talk about exponential. Then we're going to talk about gamma, the log normal, and the beta distributions. Then I'm going to walk you through example. Now, four of us want to start with the uniform distribution. I need you to follow this with the analytical mind. I need you to follow what we're going to be doing with a practical mind. Because you need to be able to understand what is behind the scene. You are seeing formula now, but I'm going to first start with what is behind the scene when I talk about uniform distribution. Look at the word uniform. Okay, the uniform means the same, so which means um, the probability of events in the sample space are equally likely. Okay, we can have an example of equally likely. When you flip a coin, you got two sides in a coin. The probability of head or tail showing up is the same. No, it's 50-50. Okay, that's uniform. Or you want to talk about tossing a die. How many sides do we have in a die? We got six sides. We got six, right? Okay, the probability of any of the numbers showing up, whether one or two or three or four or five or six, is 1/6. Okay, that is uniform. So it means the probability of any of the state space occurring is equal. That's why it's called uniform. Okay. Another example, we use that in lottery. Now, for those of you that play lottery or maybe Powerball or the like, you got 10,000 individuals that actually purchase tickets. Okay, the probability of any of them showing, winning is 1/10,000. Okay, but if you buy more than one ticket, let's say, for instance, if I buy five tickets, the probability of I winning will be 5 over the totality. Does that make sense? But If it is just one ticket, there's just going to be one out of. So, what is now? Let us now look at the statistical architecture of uniform distribution. Now that you know what we use this distribution to model, okay? Now, this distribution actually fall under the continuous function. If I'm seeking to get the probability using this distribution, then it means I'm actually going to be ready to perform an antiderivative on the probability density function, because don't forget this distribution actually fall on the continuous random variable. So we're going to be focusing on interval. I need you to take a look at this now. If I actually, the probability density function of a uniform distribution is 1 over b minus a. What is b? What is a? Okay, the a is going to be lower bound, b is going to be upper bound. Maybe I'm going to say, when I have set of data, a is going to be the minimum, and b is going to be maximum. Okay, now the probability density function of a uniform distribution is 1 divided by b minus a, which is like the length of the interval. Take a look at that. The difference between the maximum and the minimum, the reciprocal of that, that's 1 over b minus a. You know, when you take example of a gas station, let's say a particular gas station know the minimal liters, the minimal gallon they can sell, and they know the maximum gallon they can sell in a week. Okay, if the minimum gallon is A and the maximum gallon they can sell is B, the probability that they're going to sell, okay, within the interval A and B is going to be the same, which is going to be 1 over B minus A. Any question on that? So you know what B represents, you know what A represents. This is uniform distribution. Now, I'm going to walk you through an example right now. Suppose that a large conference room at a certain company can be reserved for no more than 4 hours. Okay, no more than 4 hours. Both long and short conferences, of course, you know, at times they could have conferences that is going to be short in duration. At times it could be longer. Does that make sense? So both long and short conferences occur quite often. Okay. In fact, it can be assumed that the length of X of a conference has a uniform distribution on the interval. Now, let me tell you this. In exam, if I'm going to ask you a question on continuous probability distribution, an examiner will tell you what kind of continuous probability distribution. But if I want to ask a question on discrete, you will be the one that will figure it out for discrete. You'll be the one that will figure it out, whether it's going to be Bernoulli, binomial, Poisson, hypergeometric, negative binomial, and so on like that. But for the continuous, examiner is going to tell you, just like the way I'm telling you now, that has a uniform distribution on the interval 0, 4. Now when you take a look at this interval 0, 4, A equal to 0, B equal to 4. Does that make sense? You know, the parameters of uniform distribution is A and B, right? The lower bound, the upper bound. So the lower bound here is going to be 0. The upper bound is going to be 4. Please take notes. Now, if you take a look at the picture here, I actually want to display example of a uniform. If you take a look at the probability half for whatever that happened in the interval, the probability is the same. That's what we call uniform. Okay, where the probability stay the same. Okay, that's what we call uniform. And this is an example for interval 1, 3. You know, here now, this is where A equal to 1 and B equal to 3. Okay, and if I want to form the probability, okay, if I want to form the uniform, don't forget the formula is actually 1 over B minus A. Okay, if X follow uniform with parameter A, B, if you take a look at what you're giving here, this is like parameter 1, 3. So 1, 3, if I want to form the probability now, it's going to be this. What do I have? 1 over 2. That is why you can see 1 over 2. Can you see that? That's why you see 1 over 2. 1 divided by the difference between the maximum and the minimum, okay? That is how we formulate the probability density function of uniform distribution. Any question? Okay, now with that, let's move now. Okay, if based on that, okay, they can ask you here, what is the probability density function? The probability density function is what I just compute. 1 over b minus a, or what I just need. What is my b? What is my a? B is going to be maximum, and A is going to be minimum. The moment I know that, I'm just going to. Then after that, what is the probability that any given conference lasts at least 3 hours? Okay, now, you know what happened? This particular question here, actually based on this one, actually based on this. Okay, that particular question is based on this. You know, we're talking about conference here, right? And the minimum, the maximum, you need to identify what is your A, what is your B, right? Now the question now that they are asking you now, based on that, the first question is, what is the probability density function of A? In that situation, you know your A to be 0, B to be 4. That will be 1. And if you want to use 1 over B minus A, that will be 1 over 4 minus 0. What would that be? 1 over 4. I'm done. That's how I got this. Any question? That was how I got it. What did I use? Actually use 1 over B. You know, this one was for 1 over 3. So if I want to talk about for 0, 4 now, okay, if I want to talk about 0, 4 now, so it's going to be 1 over 4 minus 0. That's 1 over 4. Okay, and when you write 1 over 4, then you need to be able to indicate the state space. Okay, the state space is going to go from 0 to 4. Okay, that is the probability density function. Now, the next question is asking you now, take a look at the next question. The next question said, what is the probability that any given conference lasts at least 3 hours? At least 3 hours. You know, at least is going to be S, greater or equal to 3. Okay, now at least 3 hours means you're going to perform an integration. That will go from 3 to what? 3 to the maximum. You see that? You see this guy here? 3 to the maximum. At least 3. It means I'm going to perform an antiderivative because they say at least 3 hours. Then it's going to start from 3. What is the maximum? The maximum is 4. So which means I'm going to integrate 1 over 4. Okay? Then I integrate 1 over 4. That is going to be, so if I want to do 3 to 4, 1 over 4 ds. So I want to integrate. This is the probability of S greater or equal to 3. Okay, don't forget, the upper bound is 4. So this is a constant function, right? It's going to be X over 4, 4, 3. That's going to be 4 over 4 minus 3 over 4. That will be 1 minus that. I think that should be 1 over 4 in a way. Okay, so which means, what does it mean? Oh, 25% of the time. What happened 25% of the time? 25% of the time, the duration of the conference will be more than 3 hours. That will occur 25% of the time. Okay, the company, the hall management, they need this information. Okay, so that's how to go about that. Now, in every probability distribution, okay, we may need the average, we may need the variance. Now for uniform, okay, if I really want to know, you know, if I want to know the mean, okay, this guy here is the same thing as expectation of X. Okay, like I want to find an average, okay, with our probability distribution. So the formula is A plus B over 2, which means if I want to determine an average in this, for this now, it's going to be 0 plus 4 over 2. All what you just need is to identify what is your A, what is your B. That is the mean. Then I want to figure out the variance. This is the formula for variance. Now, when you take a look at the mean and the variance, they are in terms of A and B. The moment you identify your A and B, you should be fine. Okay, that's how to find the mean. That's how to find the variance. And of course, if you want to find the standard deviation, all we just need to do is to find the square root of the variance. Okay? Now I'm done with the uniform. Any question? I'm done with the uniform. Go ahead. Yeah, that is a formula for the mean and the variance for uniform. If you want to know, okay? If you want to know, I'm going to tell you what to do, but you don't need that. Okay, if I have f of x equal 1 over b minus a, expected value of x is going to be a to b x f of x dx. Okay, so which is going to be a to b x 1 over b minus a dx. At the end of the day, your final answer is going to be this. Calculus.
No, I meant the 12.
Okay, now with that one, you need the variance of s equal expected value of s squared minus expected value of s all squared. So which means you need expectation of s squared is going to be a to b s squared 1 over b minus a dx. Now, this is the process. So if you go by this calculus, but you know what? Because this is not a theoretical class. And that is why I'm just giving you the formula. You don't need to derive all of these. Okay? So if you want to know how we derive that, that will be in a theoretical class. But this is a way to derive that. I need the e of s squared. Then to get the variance at the end of the day here, this is going to give me b minus a all squared over 12. That is in the hand. But you know what you need? You just need these two formula because we want to apply. Does that make sense? But we got that through calculus. This is the way. Okay, now I want to go into another distribution now. Very interesting distribution. We call it exponential distribution. What do we use exponential distribution to do? Exponential distribution is used to model waiting time before the occurrence of an event. I'm going to say that again. We use exponential distribution to model waiting time before the occurrence of an event. Okay? Now, when I say before the occurrence of an event, what do I mean by that? If I want to repair, or maybe I want to repair my computer, okay, and I take my computer to a tech that will handle that. If I want to know how long am I going to wait before it's going to fix it, that distribution is exponential. Or I actually take a look at this guy, okay, this electrical component. How long are we going to wait before this guy will not function again? Okay, if we really want to answer that question, exponential distribution can be used. Or if I go to a particular road, okay, within a week, or how long am I going to wait before the occurrence of accident? Or what is the waiting time before the occurrence of next tsunami? Or what is the waiting time before the occurrence of earthquake? Okay, if you really want to figure that out on average, how long are we going to wait? Before that occur, the distribution to use is exponential. Okay, the exponential distribution can be used to model, can also be used, apart from using it to model waiting time, we also use it to model the duration. The duration, like I said, waiting time, okay, duration, then time to failure, okay? So exponential distribution, okay, can be used to model all of that. Okay, insurance company, they can also, if they want to figure out how long are they going to wait before a customer will make a claim, that will follow exponential distribution. Because they don't want to be caught unaware. They want to predict that ahead of time. Any question? Now, you know what exponential distribution does. Now, let us now look at the statistical architecture of an exponential. Is this guy here. Okay? F of x, beta, equal to 1 over beta, equal exponential raised power minus x over beta. Okay, so the beta here, okay, is actually, is acting like a rate or scale parameter for this distribution. Now, I need to know this. I need to know beta before I can use the distribution. Okay, now the beta has to be positive, has to be greater than 0. And do you know, this is a member of a continuous probability distribution. So which means if I want to find the probability distribution using exponential, then then I need to perform an antiderivative. Now, if you take a look at this guy now, what of I actually extract this question from the textbook. You know, in this question now, okay, there's a k constant, right? And this is looking like an exponential. And they say find k such that this is a valid. So don't forget f of x dx equal to 1. And when you take a look at the s greater than 0, it means you're going to go from 0 to infinity. So you have 0 to infinity. Okay, k exponential raised to power minus 2013x dx equal to 1. Okay, now where k is a constant, I'm going to bring k out, right? Bring a k out. You're actually going to have this guy, okay, 2013x dx. Okay, now how do I perform an antiderivative, okay, on this guy? Okay, performing an antiderivative on that guy now. So performing an antiderivative on this guy now is going to be negative that 2013 x divided by negative 2013, okay, from 0 to infinity equal to 1, okay, okay. Take a look at that. Now, performing an antiderivative of that, okay. Now, if you have this guy now, you can plug in infinity, okay, k, okay, into negative, okay, 2013, okay, infinity divided by days. And of course, you know, if you take a look at what I have, because this one is down, I can just have a negative here. Okay, so 2013, okay, minus, then negative, then 2013, 0, divided by 2013, everything equal to 1. Okay, now when you take a look at this, when exponential carry negative infinity, okay, you know, it's like something that is decaying, you know, that continue to decay. You know, for those of you in physics, I don't know whether you've heard about spontaneous disintegration of atomic nuclei. When something continues to decay and decay and decay and decay, it's going to be reducing in value on the long run. This is going to be 0, right? Mathematically speaking, all this 0, so negative, negative. So I got k into exponential, and this is going to be 1 because anything is about 0, 1. So I'm actually going to have, 1 divided by 2013 equal to 1. So that implies my k equal 2013. Okay? So now here, you've done something like this before, where we actually want to figure out k constant, you know, where you're given a particular probability distribution. Okay, now let me just go into, before I go into example on exponential distribution, what is the mean and variance? If I were you, all the distribution we've been doing, make sure you write the mean and variance. They all have the formula for mean and variance. For exponential distribution, the mean is beta. The variance is beta squared. What would be the standard deviation? The square root of this guy, which is also beta. Does that make sense? So try to understand that. Now, let's now apply the exponential distribution. Okay? Suppose I actually extracted this from the textbook. Suppose that the time in hours, okay, required to repair a heat pump is a random variable x, having an exponential distribution with parameter beta equal to half. Examiner is going to give you the values of the parameters. Does that make sense? We're going to give you, but in a pure statistical class, we normally determine the parameter from the data. Okay? That is what we do in statistics, a pure statistical class. But in this class, you don't need that. The examiner is going to give you the values of the parameter, just like the way you're giving here, beta equal to half. Okay, now don't forget, I said exponential is used to model waiting time before the occurrence of an event. Here, how long do we want to wait until the heat pump is actually repaired? Now, let's take a look at the question A. What is the probability at most 1 hour will be required to, I need you to focus the board. I need everyone to focus the board so that you'll be able to see. Let me tell you this. Why I need you to focus the board? I normally want my class to be tutorial. I want my class to be, engaging. Like, I need you to sit down there and just like focus the board, ask question. Okay, even though you want to go and get a tutor, but four of us get this first-hand information. Very easy. Okay, I need you. Now, how am I going to interpret this? What is the probability? At most 1 hour. Oh, at most. It shouldn't be more than one. Okay, at most. The maximum is going to be one, but it could be less than that. Now, this is going to be equal. Now, what kind of probability distribution do I want to use? I've already been told in the question. Okay, when you take a look at the question, you've already been told that this follow exponential distribution. If I were you, what you four of us gonna do when you hear exponential distribution? I expect that you four of us, right? F of x equal this exponential this. This is the probability density function of exponential distribution. And now you've been given beta. You've been given beta to be half. Now, which means I want to perform an antiderivative. I'm going to plug in wherever I see beta. So I'm actually going to have this exponential, this, the x. What would be the range? Okay, what would be the range? The maximum is going to be 1. Don't forget it's starting from 0. Okay, all what I'm just going to do here is to perform an antiderivative. We are back at calculus again. So right here now, so this is going to be 2. So 2, 0 to 1. Okay, exponential raised to power this dx. This is going to be super easy. If I want to integrate this guy, it's actually going to be divided by -2, 0 to 1. Okay, these 2 cancel 2. You get a negative this. Okay, 0 to 1. So I'm actually going to have, okay, 1. Okay, minus this guy, 0. Okay, now take a look at this. That's going to be this plus 1. Okay, which is going to be 1 minus this guy. All what I just need to do, use your calculator here. What is exponential raised to power -2? Whatever you get, subtract from 1. I'm done. That will give you the probability that at most, okay, 1 hour will be required. Okay, that is how to figure it out. If you take a look at the second question, what is the probability that at least 2 hours? Oh, at least 2 hours. That, your interpretation, you're still going to make use of this guy here. The only thing that is going to change is just the range. At least 2 hours. How am I going to interpret that? Okay, how am I going to interpret at least 2 hours? Okay, at least, okay, 2 hours. Okay, at least 2 hours is going to be this guy here. Greater or equal to 2. Oh, it's going to start from 2. What is the highest in the distribution? Infinity. Then I'm actually going to rewrite the distribution 1 over this exponential raised to power this dx. Okay, that you're going to have 2 to infinity this 2x dx. Then you integrate again. Go ahead. How do you what?
How do you know what f of x was?
Oh, because they're going to say it in the question. Look at that exponential distribution. So whatever distribution is going to be, they will tell you. Does that make sense? Okay. Because you need to know the probability distribution before we do anything. Okay? Now, let's say the question asks, what is the average numbers of hours? Let's say the question asks, what is the average numbers of hours they're actually going to use? Am I going to wait before the heat pump? Can somebody tell me? I want to award an extra credit now. Can somebody tell me? What would be the average numbers of hours am I going to wait before they're going to repair the heat pump? Oh, I'm saying 2. I'm saying 3. I don't know whether they're going to say the same thing. Say it at the same time.
1/2.
3 of you should send me a message for extra credit. Look at me. Good job. Because you know why? The average is what? Beta. And the beta has already been given to be 1 over 2. That is going to be, so 3 of you send me a message for extra credit. Okay, and what would be the variance? Just going to be beta squared. Okay, now I'm going to go into give you another example. Okay, this is another example now. Suppose that the system contains a certain type of component whose time in years to failure, I told you, years to failure. Exponential distribution can also be used to, it's a very good distribution to time to failure. We can't, oh my God, we can't enjoy this forever. There's going to be a time it's not going to work anymore. And we need to know ahead on average. Okay, we need to know ahead on average. Okay, now the random variable t is modeled nicely by the exponential distribution. You can see now the examiner is going to tell you the kind of distribution with a mean time to failure beta equal to 5. They gave you beta again, right? If 5 of these components are installed in different systems, what is the probability at least 2 are still functioning at the end of 8 years? At the end of 8 years. What do we mean by that? The random variable here is time. Okay? At the end of 8 years, we mean time greater than 8. You see that? At the end of 8 years. So it's going to be t greater than 8. So what I'm just going to do, I'm going to write the distribution. Okay, what is my beta? We know the distribution is this, right? And you'll be given the beta to be 5. Just plugging in 5. That's what it's done here. Plugging in 5. Then integrate from a to infinity. That will be the result. You know what this guy is telling me now? The probability that at the end of 8 years, okay, that will still be functioning is just 0.2, like 20% of the time. That's what it means. Okay? Now, that is exponential. I want to go to another distribution. Oh my God. If I know exponential, then I'm going to know gamma. You know why? Gamma is a generalization of exponential. You know, whether gamma or exponential, they're still talking about the time I'm going to wait before the occurrence of event. But what is the difference between them? Exponential is going to say, exponential focus on one component at a time. One component at a time. You know, I was talking about each pump here, right? Okay, but gamma is going to talk about not just one component, but more than one component. Does that make sense? Okay, let me give you another example. The exponential is going to talk about how long am I going to wait before the occurrence of first accident. That's an exponential. Okay, take a look at this. How long am I going to wait before the occurrence of second accident or third? That's a gamma, because I'm no longer talking about first. I'm talking about second or third. So which is more or less like the relationship between exponential and gamma is more or less the relationship between geometric and negative binomial in a discrete case. Let me remind you of a discrete case. When I talk about geometric, how long am I going to wait before I record the first success? You remember geometric that I used? Did you watch a basketball game last night? No. And I say first, yes. That's a geometric, right? For negative binomial, did you watch a basketball game last night? Yes. No. Yes. No, another yes, which means the number of time I'm saying yes is more than one. Now, the same thing with the exponential and, gamma distribution. The exponential is going to say, how long am I going to wait before the occurrence of the first event? Why? Gamma distribution is actually going to say, how long am I going to wait before the occurrence of event, K event, not just first event. Okay, now that is gamma. Now let us now look at, oh my God, that is going to have two parameters, alpha and beta. I need you to do something now. When alpha equal to 1, if you take a look at that distribution, when alpha equal to 1, it will automatically become exponential. Therefore, alpha here is the numbers of such events. Let's look at that mathematically. Okay, statistics is a fun. This should be a statistical party. You get what I mean? Have fun. It's not difficult at all. The moment you really understand what each notation represents, okay, you will actually going to be fine. Take a look at this now. Let us now plug in alpha to be equal to 1. Okay, I'm actually going to have, if alpha equal to 1, I'm going to have 1 over this raised to the power that, okay, gamma 1, okay, x raised to the power 1 minus 1. Then I'm going to have this guy here. Let us analyze that. Okay, this is going to be 1 over beta. Gamma 1, okay, gamma 1 means 1 minus 1 factorial, and the 0 factorial equal to 1. And x raised to the power 0 is going to be 1. So finally, it's going to be this. What is this? This is exponential. So when alpha equal to 1, we go from gamma to exponential. Okay, which means alpha here will be the numbers of events that we're talking about, event greater than 1. If the numbers of events is 1, then you have exponential. If the numbers of events is greater than 1, then you got a gamma distribution. But you know what? We have a special name that we call alpha and gamma. I mean the parameter. The alpha is what we call the shape parameter. Because when I change the values of alpha, the distribution will be changing. Okay, and beta is a rate parameter. Okay, now, but let me tell you, the good news, if we want to use this guy to figure out the probability of the occurrence of events, okay, it's actually going to be complicated. And because of that, the good news is we're actually going to be checking this from a statistical table. Okay, I'm going to refer you to the table in the textbook. Let's take a look at and these are some functions, things that you need to know about. Here I was talking about gamma 1. Okay, so gamma 1 is 1, gamma half is that, gamma n is n minus 1 factorial. I'm still coming back to that. I said something the other time. When alpha is changing, you see different shapes, right? When alpha equal to 1 and beta is 1, you see the shape. When alpha equal to 2, so that is why alpha represents the shape parameter. When I vary the values of alpha, the shape of the distribution is going to be changing. Does that make sense? Okay, so that is what I'm just trying. And don't forget, when alpha equal to 1, what happened? When alpha equal to 1, then you have an exponential. Okay, don't forget. Okay, now let us take a look at this example. Oh, if the examiner want to give you a question on gamma distribution, examiner is going to tell you the particular distribution, and examiner is going to give you 2 parameters. They're going to give you the values of alpha. You're also going to be giving the values of beta. But before I go there, let's first look at the mean and variance of a gamma distribution. The mean is alpha beta. If alpha equal to 1, what happens? That becomes the mean of the exponential when alpha equal to 1. Okay, what is the variance? Alpha beta squared. Okay, now you can find the mean, you can find the variance the moment you know the values of alpha and beta. Now let's take a look at this example. Now I need you to listen to this. The waiting time before the occurrence of event, very useful in engineering and also very useful in biomedical study. With due respect to those who have a terminal disease. Terminal disease, they normally manage it after medical intervention. The doctor want to see what is going to be the duration of time before the occurrence of an event that I'm going to say call an ugly event of death. Okay, they use gamma distribution in the study because in the hospital they are not going to talk about one patient. If it is one patient, it's going to be exponential. If it is more than one patient, then it's going to be gamma. Now let's take a look at this example, 6.27. A biomedical study determines the survival time. So which means gamma distribution is very useful in survival analysis. Okay? Because you really want to know, after medical intervention, okay, what is the probability that a patient would live more than 10 years, more than 5 years, or within. So now in weeks, as a gamma distribution, and I also need you to pay attention to the unit of time. Here, we're talking about weeks, right? Okay, with alpha equal to 3, beta equal to 4, I told you. The moment alpha equal to 3, beta equal to 4, this is going to be gamma. Okay, when alpha equal to 1, of course, you're going to go back to the exponential. Okay, for a certain dose of a toxicant, what is the probability that a rat survived no longer than 10 weeks? You know, in clinical research, it is proved that rats has the same physiological trait as human being. You know, there is a difference between anatomic structure and physiological structure. Even though the rat and men have different anatomic structure, but they have very close physiological trait. You know, the physiological means the rate at which the organ in the body function. So, and that's why rat is being used in the clinical study. Now here, for a certain dose of a toxicant, what is the probability that rats survive no longer than 10 weeks? No longer than 10 weeks. That is at most 10 weeks. So which is going to be, if I want to solve the problem right now, what I'm actually going to do is the probability of S less or equal to 10. Okay? But if I want to do this, if I want to go using gamma, because here I was told is gamma. Okay? For gamma, okay, I have alpha, I have x raised to power this, exponential raised to power this, gamma alpha, beta raised to power alpha. So which now means if I want to find this guy now, and you've been told 3 half x, 3 minus 1, x raised to power that, divided by gamma 3, then the beta 4 raised to power 3 dx, and I want to go from 0 to 10. Oh my God, this is going to be complicated because if I simplify this guy now, I'm actually going to have this guy divided by gamma 3, and 4 raised to power 3. Let me see all this one are constant. If I'll bring them out, 4 raised to power 3, 0 to 10, s squared, e raised to power this dx. This is going to take forever. You say, what are you going to do? Now, go ahead.
Is gamma a function like e of x, or I'm just confused?
This is a gamma distribution.
So is it like alpha and beta then? Like, does it have a value to, like, is it like a variable kind of?
Actually, if you understand the gamma density, in the gamma density there is alpha, there is 2 shape parameters. You know what I've done here? I've just substituted what they gave you.
Yeah, so do you calculate the value for gamma then?
Can you say that again?
Do you calculate the value for gamma then, or is it just like a function? Right?
Oh, you mean, do you mean this guy here?
Yeah.
Oh, gamma 3 is 3 minus 1 factorial. So gamma p is p minus 1 factorial. But you know what? I'm going to save you of that time. You know what I need to do? I need you to, you don't know, you're not going to go through this. I'm going to show you, you're going to make it off the table, and that's going to be super easy. I need all highs on the board. This is super easy. Now, let me show you how you're going to do that. Now, and I'm going to use this example. All eyes on the board. This is critical. All eyes on the board. Some of you are still looking at the computer. I want all eyes on the board. I know this is difficult. I know it is difficult. But the moment you focus the board, it's going to be so easy. All eyes on the board. Let's take a look at it. We are not going to go through all. This is going to take forever. This is complicated. We want to make use of a table. But what I just need from you, I need your eyes on the board. Let's take a look at this. In a biomedical study, right now, you're giving alpha to be 5, beta to be 10. And the question now is, what is the probability that a rat survived no longer than 60 weeks? No longer than 60 weeks. No longer than 60 weeks means, what I want to do this time around, what I want to find is going to be probability of S less or equal to 60. And, if I go by this, it's going to be complicated, right? How are we going to do it? Just take a look. You know, they say no longer than 60 weeks. What you're going to do is, we want to, four of us reparameterize. And if you take a look at this guy, that is what we're supposed to do by calculus, right? What have we done there? We substituted, right? You know, we want to make use of the formula here, right? To figure it out. But let me tell you this is what you're going to do. We're going to make use of a table. That value that you are giving, you're actually going to perform this to be able to make use of a table. What was the value given? Please focus. What was the value given? 60, right? You follow do 60 divided by beta. What is beta given? Let's go back. What was the beta given? The beta is 10, right? The beta is 10, right? 60 divided by beta. What is 60 divided by 10? 6, right? You know what I'm going to check in the table of gamma? I will check 6 against the values of alpha. Take a look at this guy. What do you see here? This is what I want to check from the table. Where do I get my 6? Where do I get my 6? The value given divided by beta, 60 divided by 10, that would be 6, comma, the values of alpha. You know alpha is 5, right? Now, I'm going to show you the table now. Okay? If I check this in the table, it's going to give me this. I'm done. I'm done. Now, let's see how we're going to check it in the table. We want to check from the gamma table. Okay? I'm going to, give me 1 second. I'm going to discard this. Then I'm going to go to the, now I need you to be focused. What page in the textbook? 788. Okay? What do you see? Table 8.23 for gamma. Okay? What do I want to check? I want to check for 6 here against 5, alpha. You know, it was, how do I get it 6? 60 divided by the values of beta. Don't forget, 60 divided by 10, that gives you 6. I'm going to check 6 against 5 now. Let's see. Give me 1 second. I'm going to write now. 6 against 5. What is the answer? I'm done. Go ahead.
We get this table in exams.
Yes. You will get all the table in the exam. Yep. Okay. Is it not easy? Very easy. You don't need calculus here. We don't want to waste time. Now, I'm going to go into the question again. What do you see now? Done. Done. Just make it on the table. Look at another question. This time around, you're giving alpha, beta. Then changes were made to tighten the quality control requirement. Following these changes, 20 months passed before the first complaint. Does it appear as if the quality control tightening was effective? 20 months passed. That's greater than 20. 20 months passed. Now, greater than 20, but which means I want to find the probability of S greater or equal to 20. You know, if I want to find the probability of greater, it's going to be 1 minus. You remember what we always do. In the table, you only have less than, right? You have less than in the table. If you want to do greater than, whatever you check from the table, you're going to subtract from 1. Now, let us see now. What is the first thing we're going to do? We're going to do 20. 20 divided by what? Beta. What was the beta? 4. What is 20 divided by 4? 5. Right? 5. What is the values of alpha? 2. I will just go to the table and check 5 and 2. You remember the way I check 5? The way I checked from the table the other time? Will that give me this from the table? Then 1 minus that is going to give me the result. I'm done. 1 minus that will give me the result. Okay? I'm not going to start the next distribution today. I think I'm going to start on Wednesday. Is there any question before I go? always make use of the table. Okay? Make sure you stay safe and have a lovely day. Bye for now, everyone.